We built the fastest vehicle of all time, not to travel the furthest, but to do the exact opposite, to get closer to our nearest star, the Sun, and that is the irony. Because this inward journey became the most painful proof that we can never escape. We use the Sun's gravity to reach 430,000 miles per hour. But that speed is nothing but the universe laughing at us. A journey to the nearest star would take 6,600 years. A mission started by the ancient Sumerians would only be arriving now. But that's not even the greatest irony. The real irony is that the answer was not hidden in faster engines, but in the formulas of a 26-year-old clerk working in a patent office in 1905. If you want to see how that formula, which destroys distance by bending time, extends a human life into infinity, subscribe. Because now we're going to break the laws of physics. We begin. For 200,000 years, humanity was stuck at the speed of a horse. Then, in just 66 years, we propelled the Apollo astronauts to the moon at 25,000 miles per hour. It seemed like there were no limits. But we were terribly wrong. Today, humanity's fastest object orbits the Sun at 430,000 miles per hour. But even this mind-boggling speed is a cosmic joke. Because, at this speed, reaching the nearest star would take you exactly 6,600 years. If you travelled for a lifetime, you would only cover 1% of that distance. But that's not the most disturbing part. Hidden within this wall that we thought physics had imprisoned us in, there is a secret door, a door that can fit entire galaxies into a single lifetime. If you too want to see how deep into the cosmos a single human life can reach, join this channel. Because everything you know is about to change. For years, we thought space travel was just an engineering problem. Better engines, more efficient fuels, smarter designs. Humanity had been confined to the speed of a horse for 200,000 years. But then, in just 66 years, we went from supersonic jets to rockets that reached the moon. Our progress was dizzying. It seemed like there was no limit. But on a cosmic scale, this was nothing more than a bitter illusion. Because our greatest achievement also became the clearest proof of how trapped we really were. We know now the real obstacle is not in our engines, but in the very fabric of the universe itself. The most concrete evidence of this truth is screaming around the Sun right now. Its name is the Parker Solar Probe, the fastest object ever made by human hands. Its speed exceeds 430,000 miles per hour. It's almost impossible to visualize this speed. So, think of it this way. If you were moving at this speed, you would cross the United States from coast to coast in less than 25 seconds. You could blink once in New York, and by the time you opened your eyes, you would have already passed Los Angeles. This is a triumph of engineering, billions of dollars in investment, thousands of scientists, and decades of accumulated knowledge are embodied in this piece of metal. But this victory is not even a whisper by the brutal standards of the universe. Because Kiasi, this incredible speed is still not enough to take us to our nearest neighbour, Proxima Centauri. That journey would take exactly 6,600 years, meaning if you had set off when the ancient Sumerians invented writing, you would only be arriving now. This is why this speed is an illusion. This speed does nothing more than allow us to crash into the walls of our cosmic prison faster. So where is the problem? Why are we so helpless? Because we have never escaped the basic technology we've been using for thousands of years. From the Parker Solar Probe to the Apollo rockets that went to the moon, even to the first Chinese fireworks that lit up the sky 1,000 years ago. They all work on the same principle. You throw something backward, you go forward. Newton's third law, elegant, simple, and devastatingly inadequate for interstellar travel. When the Apollo astronauts returned from the moon, they reached a speed of about 25,000 miles per hour. It was the highest speed a human had ever achieved until that day. The Parker probe is much faster, yes. But it is just a more powerful version of the same primitive idea. We are just burning the fire more intensely. That is why this technology is a dead end. Because no matter how powerful an engine you build, you slam into a mathematical wall known as the tyranny of the rocket equation. This wall was formulated in 1903 by the Russian scientist Konstantin Tsiolkovsky, and what it said was terrifyingly simple. The final speed a rocket can reach depends on how fast its fuel is ejected, and what proportion of the rocket's total mass is fuel. For chemical fuels, this is a disaster, because even when you burn the most efficient rocket fuel, hydrogen and oxygen, there is a limit to the exhaust velocity of the resulting water vapor molecules. They cannot go faster than 4.5 kilometers per second. This is not an engineering limit. This is a law of chemistry, and this equation turns our dreams into a nightmare. The math shows us this. To accelerate a small probe of just 1,000 kilograms to 1% of the speed of light using chemical fuel, the amount of fuel you would need exceeds the total mass of the observable universe. This is not an exaggeration. The mass of the Earth, the Sun, or all the stars in our galaxy is not enough. Even if you converted every single atom in the universe into fuel, you couldn't get a small car to 1% of the speed of light. The rocket equation punishes every demand for an increase in speed with an exponentially increasing amount of fuel. There seemed to be a way to escape this tyranny, the planetary slingshot effect, a gravity cheat. As you pass by a planet, you steal a piece of its orbital energy. You accelerate without burning fuel. The Voyager probes used Jupiter and Saturn to launch themselves out of the solar system. The Parker probe also used Venus to reach its record speed. It sounds like a great solution. But this too is a deception, because the number of planets in the solar system that can help you is limited. Each maneuver takes years. Even the energy you can steal from our biggest helper, Jupiter, is limited. The maximum speed you can reach with a careful gravitational ballet lasting decades is maybe 150,000 miles per hour. Even that means a journey of tens of thousands of years to the nearest star. As you can see, the problem is not a simple speed problem. The problem is at the most fundamental level of physics. Our fastest vehicle is an illusion. Our most reliable technology is a 1,000-year-old idea. And even our smartest escape plan only gets us as far as the prison yard. These equations seem to have trapped us. But what if there is something we haven't noticed? Deep inside these equations, in the depths of this brutal mathematics, what if this whole problem seems unsolvable? Because we have been asking the wrong question. Because the wrong question was, how do we go faster? We pursued this question for centuries. Bigger explosions, more efficient engines. But the universe had a secret. And that secret was revealed in 1905 by a 26-year-old young man working quietly in a patent office in Bern. His name was Albert Einstein, and he did not ask, how do we go faster? He asked a much more fundamental question. What would you see if you could travel alongside a beam of light? This innocent question demolished 300 years of physics and showed us that the wall we thought had imprisoned us was actually a door. The key to this door was an almost trivial-looking proposition by Einstein. The speed of light, in a vacuum, is constant for everyone who observes it. It is crucial to understand the revolutionary power of this sentence. Whether you're standing still on Earth or racing through space at half the speed of light, when you turn on a flashlight, you will always measure the speed of the light coming from that flashlight as exactly 186,282 miles per second. This is not a technology limit. This is a fundamental rule of reality. It feels counterintuitive. Because, or in normal life, if you throw a ball forward from inside a moving car, the speed of the ball adds to the speed of the car. But this is not true for light. It is always the same speed. So how is this possible? If the speed of light has to stay the same for everyone, then something else had to change, to stretch, to bend. Einstein realized that something was time itself, and that realization changed everything. This is the phenomenon called time dilation, and it is the most mind-bending but most robustly proven truth of modern physics. A moving clock runs slower than a stationary clock. This is not a metaphor. This is a law of physics. Time is not a universal river that flows at the same rate for everyone. Your speed determines how fast time flows for you. At everyday speeds, this effect is so small it is unnoticeable. On an airplane trip, you age just a few billionths of a second less than someone who stayed on the ground. But when your speed begins to approach the speed of light, the magic begins. If you travel at 50% of the speed of light, every 1 year that passes for you corresponds to about 14 months for someone on Earth. Noticeable, but not revolutionary. Increase the speed to 90%. Now, 1 year for you is 2 years and 4 months on Earth. When you return, your grandchildren will have aged. Increase the speed to 99%, and for every 1 ship year, 7 years pass on Earth. This is the formula for escaping the cosmic prison. Because the problem is no longer about covering the distance faster. The problem is about shortening the time that passes for you during the journey. The mathematical tool that calculates this effect is called the gamma factor. This number is a brutal but fair measure of how much time slows down and how much mass increases as your speed increases. As your speed approaches the speed of light, the gamma factor increases exponentially. At 99.9% of the speed of light, gamma exceeds 22. This means 1 year on the ship is equal to 22 years on Earth. Every 9 you add dramatically magnifies this effect. At 99.999% speed, gamma exceeds 223, and now the journey to the stars is redefined. Vega, one of the brightest stars in our sky, is 25 light-years away from us. With a classic rocket, it would take hundreds of thousands of years to get there. But if you go at 99.9% speed, because the gamma factor is 22, the journey for you will take just a little over 1 year. When you return, Earth will have aged 50 years, but you only 2. This is not a theoretical exercise. This is how the universe itself works. And so the problem changed completely. The speed of the Parker probe, the tyranny of the rocket equation, the gravitational tricks of the planets, all of these were answers to the old, wrong question. The real answer was not in engines, but hidden in the very nature of time itself. Einstein had given us a map. This map showed that the closer you get to the speed of light, the more you can slow down time, and therefore, you can fit unimaginable distances into a single human lifetime. This was no longer an engineering challenge. This was an invitation from physics itself. The potential to go not just out of the solar system in a lifetime, but to the center of the galaxy, or even to neighboring galaxies like Andromeda, was hidden in these equations. That was the theory. A mind-boggling, but mathematically sound theory. But what about the practice? What would it be like inside an accelerating ship? What would the universe outside look like? And most importantly, how would this bending of time play with a passenger's reality? We know the theory, we hold the key. But now it is time to open that door and see what awaits us on the other side. And now comes the real shock. Because the theory is over. The ink on the equations is dry. We are now inserting the key that Einstein gave us into the lock and opening the door wide. What awaits us on the other side is a series of discoveries that push the limits of the human mind, shatter our intuitions, and redefine what a lifetime means. Here are the findings. Our first discovery begins with one of the brightest jewels in our sky, Vega. That bright bluish-white star you can see on most nights with the naked eye. It's about 25 light-years away from us. This means it takes 25 years for its light to reach us. Even humanity's fastest probe, Parker, would take hundreds of thousands of years to get there. This seemed like a wall of impossibility. But this wall is a sandcastle before time dilation. If you can reach 99.9% of the speed of light in a ship, your gamma factor exceeds 22. What does this mean? For observers on Earth, your journey will take about 25 years. This is an unchangeable fact of physics. But for you, in the protected time bubble inside the ship, the journey takes only and only a little over 1 year. You can go. You can discover a planetary system there, and you can come home. While this whole adventure takes 2 or 3 years for you, the Earth you left behind has aged a full 50 years. This was not supposed to happen. A distance that should not fit into a lifetime suddenly becomes as accessible as a weekend getaway. Because you did not conquer distance, you conquered time. But that was just a stroll through our neighborhood. The real journey begins now, because we are choosing a bigger target, the heart of our galaxy, that chaotic, star-boiling region at the center of the Milky Way, which houses a supermassive black hole of 4 million solar masses at its core. The distance is a full 26,000 light-years. Even saying this number is difficult. The entire history of humanity is not enough to cross this distance. It seemed physically impossible until we increased our speed a little more. Imagine reaching 99.9999% of the speed of light. Your gamma factor is now over 700. For an observer on Earth, it still takes 26,000 years for you to reach that black hole. But, for you, for the passenger, time bends so much that this massive journey fits into just 37 years. Think about it. You leave Earth at 25. You arrive at the threshold of the galaxy's monster when you are 62. In the span of a person's career, you have crossed the cradle of humanity from one end to the other. This was against our theories. Galaxies were massive structures to be lived in, but never to be crossed from end to end. But the equations did not lie. A human lifetime was enough to traverse the entire galaxy, and now, the absolute peak, the moment logic fails, because we are not content with just leaving our galaxy. We set our sights on our closest neighbour, the Andromeda Galaxy. It's 2.5 million light-years away from us, a separate island universe, home to 1 trillion stars of its own. This distance is no longer astronomical, it's geological. Light itself spends 2.5 million years crossing this void. This was the absolute limit, uncrossable by any technology, any imagination. But what if we could increase the gamma factor to millions? Theoretically, it is possible. What would happen then? For someone watching from Earth, your journey takes 2.5 million years. In that time, humanity could evolve, go extinct, or transform into a completely different species. But, for you, the passenger on the ship, time slows down so incredibly that your journey to Andromeda takes only 2.5 years. Yes, 2.5 years. You cross the intergalactic void, which light takes millions of years to cross, in less time than it takes to get a university degree. This should not have been possible. This was like cheating the rules of the universe. The laws of physics should not have allowed this. But they did. Einstein's equations told us that we could fit not just stars, but entire galaxies into a single lifetime, to go to a star in a year, to reach the heart of the galaxy in 37 years, to arrive at a neighbouring galaxy in 2.5 years. These are no longer just numbers, they are the map of humanity's potential future. But reading this map is not easy. These journeys are possible in theory. But what about in practice? What does travelling at these unimaginable speeds do to a person's body and soul? And what is the dark paradox that no one talks about, caused by this brutal bending of time? Because the theoretical possibility of these journeys brings with it a series of disturbing and strange consequences, and the dark paradox that no one talks about is the most brutal twist of time, known as the twin paradox. This is not just a thought experiment, it is an inevitable reality that every astronaut embarking on such a journey will have to face. The paradox is this: imagine two identical twins, Alice and Bob. Alice boards a relativistic ship and travels to a star 20 light-years away at 90% of the speed of light. Bob stays on Earth. For Bob on Earth, Alice's journey out takes about 22 years, and her return trip takes another 22 years. Bob ages a full 44 years while waiting for his twin to return. He greets his sister, whom he bid farewell to as a young man, in his retirement age. But, for Alice on the ship, reality is completely different. At 90% of light speed, the gamma factor is about 2.3. Therefore, each leg of the journey that takes 22 years feels like only 9.5 years to her. She has aged only 19 years. When she returns, her twin, born on the same day, is 25 years older than her. While the first grey hairs appear in Alice's hair, Bob's hair has turned completely white. This should not have happened. Physics should not have allowed time to separate siblings so cruelly. But it did, because Alice experienced acceleration, meaning speeding up and slowing down. This asymmetry is the breaking point that determines for whom time flows slower, but this is just the beginning. Because relativistic speeds fundamentally change not just your perception of time, but also your perception of the universe. As the ship accelerates, the things you experience visually are unlike anything else. The light coming from the front of the ship is compressed by an effect called blue shift. The stars lose their normal colors. They turn blue, then violet, then ultraviolet, and finally into X-rays. The familiar constellations in front of you become an invisible source of radiation that you can only see with special instruments. The universe behind you suffers the opposite fate. It is stretched by the redshift effect. The stars behind you first turn red, then infrared, and finally fade away, becoming radio waves. For you, the universe transforms into a narrowing, bright tunnel ahead, and an absolute darkness growing behind. When you reach 99% of the speed of light, the entire observable universe is squeezed into a narrow circle of just 16 degrees at the nose of your ship. As you accelerate further, billions of galaxies converge into a single bright point in front of you. This is a farewell to the universe, and the most dangerous aspect of this farewell is the interstellar medium itself. Because space is not as empty as we think. On average, there is about one hydrogen atom in every cubic centimeter. At low speeds, this is nothing. But at relativistic speeds, this sparse gas turns into a deadly radiation bombardment. Each hydrogen atom hits your ship with the energy of a cosmic ray particle. As your speed increases, the energy of these collisions increases exponentially. The ship is battered as if by billions of miniature atomic bombs per second. This is a storm that will erode even the most advanced shields over time, destroy electronic systems, and tear biological tissue apart. This journey is not just a journey of time and space. It is also a passage through a hell created by the most fundamental particles of the universe. This is the price that physics wants you to pay. In exchange for reaching the stars, the universe takes not only your youth, but also your safety, the bending of time, the separation of twins, the transformation of the universe into a visual tunnel, and the conversion of space into a deadly radiation field. All of these are the inevitable consequences of Einstein's equations. They open a door for us, and at the same time, they tell us how dangerous and strange it will be to pass through that door. So how does this work? I mean, yes, the equations are there. But what kind of engine could propel a ship to 99.9% of the speed of light? Where would this energy come from? Because, as elegant as the physics that makes this journey possible, is the technology required to achieve it must be just as monstrous. So, how does it work? Because Einstein's equations are an invitation, not a vehicle. They tell us we can bend time, but they don't tell us how to do it. To answer that invitation, to propel a ship to near-light speeds is the greatest engineering challenge in human history. It requires escaping the tyranny of the rocket equation and dancing at the most fundamental levels of energy and mass. Let's slow the tempo down a bit. Let's descend from the shocking discoveries to the cold, raw, hard physics of the monstrous technologies that could make these discoveries possible. This is the science of using the power not of engines, but of the universe itself. The first and perhaps most audacious idea is to ride on the back of nuclear explosions to the stars. This concept is called nuclear pulse propulsion. And the idea is as simple as it is insane. Just as a skateboarder pushes himself forward with a series of exploding firecrackers, this system works by detonating controlled nuclear bombs behind the spacecraft. This idea was seriously studied in the late 1950s under the name Project Orion. Engineers planned to place a giant pusher plate at the back of the ship. This plate would absorb the shockwave from each nuclear blast. The plasma created by the explosion, millions of degrees hot, would strike this plate and push the ship forward. Giant shock absorbers placed between the pusher plate and the crew cabin would convert these violent impacts into a gentle acceleration that astronauts could withstand. This was not a fantasy. The brightest minds of the era, like Freeman Dyson, worked on this project, and small-scale tests with chemical explosives proved the concept worked. According to calculations, a modest Orion ship using atomic bombs could reach 3 to 4% of the speed of light. More advanced hydrogen bomb designs could increase this speed to 8 to 10% of the speed of light. This is hundreds of times the speed of the Voyager probe. It is a speed that is impossible with chemical rockets. Why is it so effective? Because It solves the biggest enemy of the rocket equation at its root, fuel efficiency. A chemical rocket only converts its fuel's energy into heat. Orion, on the other hand, converts the raw destructive power of a nuclear bomb just to send E equals mc squared itself directly into thrust. This is the most elegant application of brute force. But even nuclear bombs come with a limit, because you still have to carry the fuel, the bombs, on the ship. This is where a second idea comes in: nuclear fusion propulsion. This is an attempt to take the sun's own energy generation mechanism and fit it inside a rocket engine. Instead of external explosions like nuclear pulse, this aims for a controlled and continuous thermonuclear reaction. Just as a car engine runs on continuous small gasoline explosions, a fusion rocket would create miniature suns by fusing hydrogen isotopes like deuterium and tritium. The helium and high-energy neutrons produced during this fusion are ejected through a magnetic nozzle. The exhaust velocity of these particles is many times higher than the exhaust of chemical rockets, and even roughly twice that of nuclear fission rockets. Engineering studies like Project Daedalus showed that this technology could reach 12% of the speed of light. A giant 54,000-ton ship could reach this speed with continuous firing for 2 years and arrive at Barnard's star 6 light-years away in 50 years. This is still longer than a human lifetime. But we're now talking about decades, not tens of thousands of years. The power of this technology comes from the energy density of the fuel. Nuclear fusion converts about 0.7% of its mass into energy. This rate is thousands of times more efficient than chemical reactions. This is a major victory against the tyranny of the rocket equation. With less fuel, you get much more speed. Even fusion is still stuck with the problem of carrying fuel. So what if we didn't carry the fuel at all? This question brings us to the third and most elegant solution: beamed energy propulsion, or laser sails. The concept is based on completely cheating the rocket equation. A rocket has to carry both its engine and its fuel. This is a vicious cycle where you have to accelerate the fuel you carry to accelerate. The laser sail breaks this cycle. You leave the power source, the giant laser, on Earth. You send only a gram-weight, ultralight sail and a star chip attached to it into space. Just as the wind pushes a sailboat, a 100-gigawatt laser beam fired from Earth pushes the sail with the momentum of the photons hitting it. The Breakthrough Starshot project aims to accelerate a probe of just a few grams to 20% of the speed of light in just 10 minutes using this method. At this speed, the journey to Alpha Centauri would take only 20 years. The beauty of this system is its efficiency. The ship is almost massless, the energy source is almost limitless and stays on Earth. This is a complete bypass of the rocket equation. But this elegance has a fatal flaw: you can't brake. The laser pushes from behind, but there is no laser at the destination to slow you down. Therefore, the Starshot project has to fly past the Alpha Centauri system like a bullet at 20% of the speed of light. For manned travel, this is a catastrophe. Nuclear pulses, fusion engines, laser sails. All of these are based on different physical principles that could take us to the stars. Each has incredible advantages and equally terrifying challenges. One is brute force, another a controlled sun, and the third the lightest touch of the universe. But they all try to answer the same question: how can we convert mass into energy and speed in the most efficient way? And the answer to this question may lie not in a single technology, but in a combination of all of them. But what if, beyond all these methods, there is a final, most powerful, and most dangerous fuel that physics offers us? What if we could convert 100% of the mass into energy? And yes, such a fuel exists. It is the final gift physics offers us, and also its greatest curse. Its name is antimatter, because it is the only thing that can convert 100% of mass into pure energy. When a particle of matter meets its antimatter equivalent, they both completely annihilate, leaving behind only a burst of energy consisting of gamma rays and other fundamental particles. This is the most perfect fuel imaginable. Just as a key fits perfectly into a lock and opens a giant door as soon as it turns, antimatter is the key that unlocks the equation, E equals mc squared. When 1 gram of antimatter annihilates with 1 gram of normal matter, it releases an amount of energy equivalent to the explosive power of the atomic bomb dropped on Hiroshima. This is about 180 trillion joules. This number is so large that it is 140 times more dense than our most efficient energy source, nuclear fusion. Comparing it to chemical rockets is meaningless. Antimatter is thousands of times more powerful. Therefore, an antimatter rocket completely shatters the tyranny of the rocket equation. The exhaust velocity is very close to the speed of light itself. This means you could theoretically propel a ship to 70%, 80%, or even higher percentages of the speed of light. At 70% of light speed, a journey to the star Epsilon Eridani, 10.5 light-years away, would take 14 years for an observer on Earth, while it would take only 9 years for the passenger, thanks to time dilation. This opens the door to exploring another star system within a human lifetime and maybe even returning. Antimatter is the key to the relativistic journey the equations promised us. But this key comes with a price, and that price is so high, it is almost insurmountable. Because antimatter is not found naturally in the universe. Every single particle of it must be produced in particle accelerators like CERN, at the cost of immense energy. And this production process is horrendously inefficient. With our current technology, the energy we spend to produce 1 gram of antimatter is billions of times more than the energy that antimatter will release when it annihilates. Producing the antimatter needed for just 1 interstellar mission would require more than the total energy consumption of human civilization for hundreds, perhaps thousands of years. And that's just the production problem. There is also storage. Antimatter annihilates the moment it touches normal matter. So, you have to suspend it in the air, in a perfect vacuum, using magnetic fields, so that it never touches the walls of its container. The longest we have ever been able to store antimatter is only a few hours. An interstellar journey, however, would take decades. These problems leave antimatter in the realm of science fiction for now. The physics works, but the engineering is not even in its infancy. It's like having the key to a sports car. But neither the car nor the roads to drive it on have been invented yet. This is why scientists have investigated another or a stranger idea, the Bussard ramjet. This idea promised to solve the fuel problem in the most elegant way. Don't carry the fuel, collect it on the way. Proposed by Robert Bussard in 1960, this concept imagines a spaceship creating a giant magnetic field, scoop, thousands of kilometers wide, in front of it. This magnetic scoop would collect the sparsely distributed hydrogen atoms in the interstellar medium and direct them into a fusion reactor at the back of the ship. Just as a jet engine takes in air from the front and burns it to push out the back, a ramjet would collect and burn the hydrogen of space to provide continuous and theoretically infinite acceleration. This idea was revolutionary because it eliminated the fuel mass limit. Since the ship collects its fuel as it travels, it could arbitrarily approach the speed of light by continuously accelerating. This was like the holy grail of relativistic travel. But detailed calculations revealed a bitter truth. The magnetic scoop itself, by interacting with the particles in space, created more drag than the thrust the engine could produce. In other words, the ship had opened a cosmic parachute so large that its engine could not overcome it. This elegant dream collapsed under the weight of its own physics. But what if there is a more speculative way? One that even pushes the boundaries of physics? What if we don't have to pass through space to get from one place to another? This question brings us to the Alcubierre drive, the warp drive concept. This is a quirk allowed by Einstein's equations of general relativity, but its existence in nature is unknown. This idea is based not on moving the ship itself, but on moving space-time itself. You warp and compress the space in front of the ship while expanding the space behind it. The ship, like a surfer on this space-time wave, is carried forward by space itself without moving at all. For an observer inside the ship is stationary and no laws of physics are violated. But this warp bubble can move space so fast that faster-than-light travel becomes theoretically possible. However, for these equations to work, they require exotic matter with negative energy density. This is a type of matter that repels gravity, and we don't know if it exists. And even the most optimistic calculations show that moving a small ship would require an amount of this exotic matter equivalent to the mass energy of Jupiter. It is a fascinating mathematical possibility, but for now, It is far from a physical reality. Nuclear pulses, fusion rockets, laser sails, antimatter and warp drive. These are all humanity's attempts to escape its cosmic prison. Each offers a different key. One is the key of brute force, another of efficiency, and yet another of manipulating the very fabric of reality. But the truly exciting thing is not what these technologies can do on their own. The truly exciting thing is that they give us permission to ask the ultimate question. If we had a perfect propulsion system, if energy was not a problem, how far could a human lifetime extend? It's time to set engineering aside and explore the absolute limits allowed only by physics and the structure of the universe itself. And now comes the true miracle. Because the engineering is finished, the theories are silent. We now have an imaginary propulsion system. Energy is unlimited. Acceleration is as easy as pressing a button. This is a future where humanity has perfected technology. And in this future, we ask only one question. With this perfect ship, how far into this universe can a human lifespan of 80 years reach? The answer exceeds all expectations. It leaves all dreams behind. Because now we have reached the climax. It is no longer about going to a star system. It is now about the breathtaking, mind-bending, and almost divine mathematics of fitting an entire cosmos into a single lifetime. The tempo is increasing. Get ready. The first step, the most modest one, but still a revolution. Our speed, 99% of the speed of light. This is the threshold where the gamma factor reaches 7.1. Our travel time, 50 subjective years. Our passenger will age 50 years while on the ship. So where can they get to in those 50 years? The answer, 350 light years. This isn't a number. This is a world. The sphere within this radius encompasses about 50,000 star systems. Inside are hundreds of stars similar to our Sun, and thousands of confirmed planets orbiting these stars. 350 light-years includes some of the most familiar structures in our sky. The Pleiades star cluster is just beyond this distance. A round trip there would take the passenger about 126 years, while for Earth, almost 900 years would pass. How is this possible? Because we're no longer trying to go faster. We're slowing down time. For the first time in history, a human lifetime is long enough to visit thousands of star systems. This is humanity's first real step into the stars, a discovery. But this is only the beginning, because we can go faster. The second step. Now reality bends. Our speed, 99.9% of the speed of light. Our gamma factor has jumped from 7.1 to over 22. Time dilation is no longer linear, it's exponential. Our travel time is still the same, 50 subjective years. So where have we reached now? The answer, 1,100 light years. Understand the magnitude of this leap. We increased our speed by only 0.9%, but our range tripled. This is the theory in its wildest form. What is in an area with a radius of 1,100 light-years, millions of star systems, and potentially tens of billions of habitable planets? One of the most iconic sights in our sky, the Orion Nebula, is about 1,300 light-years away from us. So, at this speed, within a human lifetime, you can go to that cosmic cradle where new stars are born. You can see newly forming planetary disks. You can witness thousands of newborn stars illuminating gas and dust. These are things seen from Earth as only faint smudges. But you are there. One human life. A single sequence of heartbeats. And you're inside one of the galaxy's most magnificent birthplaces. This should not have been possible. Physics should not have allowed a lifetime to encompass such a vast distance. But it did. Because Einstein's equations offered us the universe's greatest trick. The third step, logic fails. Words are insufficient. Our speed, 99.9999% of the speed of light. The number of nines on the speedometer has increased, and with each 9, the universe has shrunk for us. Our gamma factor is no longer 22, not 223. It's a full 707. Time is no longer slowing down. It's almost stopping. Our travel time has not changed. Still 50 subjective years. Where have we arrived in these 50 years? Are you ready? The answer: 35,000 light years. This means crossing the center of our galaxy and reaching the other side of the Milky Way in a single human lifetime. This is the greatest record in human history. Think, one person leaves Earth, crosses our entire galaxy, that massive spiral structure of hundreds of billions of stars and dark matter from end to end. And this whole journey takes only 50 years for them. When they reach the end of their life, they are tens of thousands of light years from home, in a region of the galaxy no human has ever seen before. How can this be possible? What law of physics does this fit into? This is not the realm of science, but almost of mythology. This journey, fitted into one lifetime, makes Odysseus's journey look like a morning walk. The scientific world was shocked when these numbers were first calculated, because this showed that the galaxy was no longer an obstacle, but had become a playground. The fourth step. And now, we open up to the cosmos. Our galaxy is now small for us. We set our sights on other galaxies, those island universes, our destination, the Andromeda Galaxy. Our nearest major neighbor. The distance, 2.5 million light years. This is a distance the mind cannot grasp. But not for us, because we continue to accelerate. Our gamma factor is no longer in the thousands, but in the tens of thousands, exactly 50,000. Time has slowed down so much that a second is like a lifetime. Our travel time is again 50 subjective years. In these 50 years, we arrive at Andromeda. Feel the weight of that sentence. In 50 years, 2.5 million light years, you celebrate 50 birthdays on the ship. On the Earth you left behind, 2.5 million years pass. The human species on that planet is now in an unrecognizable state. Maybe it doesn't even exist. But you exist, and you are in Andromeda. You're inside a galaxy of 1 trillion stars, bigger than the Milky Way. You're orbiting a larger supermassive black hole. You're under constellations never seen before. This is the greatest discovery, the greatest journey, and the greatest exile in history, because you can never return. Even if you did, there would be no home to return to. This is the most brutal trade-off in physics. It gives you the universe, but in return, it takes everything you belong to. These 4 steps have redrawn the boundaries of a human lifetime. Star clusters, nebulae, the galactic center, and neighboring galaxies all have theoretically become reachable within the lifespan of a single conscious being. But this is not the end of the story, because the universe is much larger than Andromeda, and our perfect ship can still accelerate. So what if we push everything to its absolute limit? What if we try to calculate the absolute, final, physical limit of a human lifetime? And yes, we can push everything to its limit. Because the human mind knows no bounds. We have a perfect ship, and now, with it, we will challenge not just neighboring galaxies, but the universe itself. We will find the absolute limit, the furthest point a single lifetime can touch. And that point is further than even the wildest science fiction writers could have imagined. This is the moment a human becomes a cosmic god. The 5th step, cosmic cities. We're no longer concerned with individual galaxies. We set our sights on galaxy clusters, the mega structures of the universe. Our target, the Virgo cluster, the nearest major galaxy cluster to us. It contains more than 1,300 galaxies, a galactic metropolis. Its distance is a full 54 million light years. This number is measured not by human history, but by the history of life on Earth. Dinosaurs were walking on Earth when this light began its journey. This is an insurmountable temporal abyss. But not for us, because our gamma factor is now in the millions, 1,080,000. Time has almost completely frozen for us. Our travel time is still and always the same, 50 subjective years. In these 50 years, we arrive at the Virgo cluster. When we get there, the Earth we left behind has aged 54 million years. But you are only 50 years old, and you look around. What you see is not a single sky. It's thousands of skies. In every direction, hundreds of galaxies as large as or larger than the Milky Way are shining. They're orbiting each other. They're colliding with each other. You're in the midst of a cosmic chaos and creation. This is the greatest record in history. For the first time, a human has left their local galaxy group and witnessed the large-scale structure of the universe. How can this be possible? What law of physics can fit geological timescales into the lifespan of a mammal? This is where science ends and philosophy begins. An interstellar journey, however, would take decades. These problems leave antimatter in the realm of science fiction for now. The physics works, but the engineering is not even in its infancy. It's like having the key to a sports car. But neither the car nor the roads to drive it on have been invented yet. This is why scientists have investigated another or a stranger idea, the Bussard ramjet. This idea promised to solve the fuel problem in the most elegant way. Don't carry the fuel, collect it on the way. Proposed by Robert Bussard in 1960, this concept imagines a spaceship creating a giant magnetic field, scoop, thousands of kilometers wide, in front of it. This magnetic scoop would collect the sparsely distributed hydrogen atoms in the interstellar medium and direct them into a fusion reactor at the back of the ship, just as a jet engine takes in air from the front and burns it to push out the back. A ramjet would collect and burn the hydrogen of space to provide continuous and theoretically infinite acceleration. This idea was revolutionary because it eliminated the fuel mass limit. Since the ship collects its fuel as it travels, it could arbitrarily approach the speed of light by continuously accelerating. This was like the holy grail of relativistic travel. But detailed calculations revealed a bitter truth. The magnetic scoop itself, by interacting with the particles in space, created more drag than the thrust the engine could produce. In other words, the ship had opened a cosmic parachute so large that its engine could not overcome it. This elegant dream collapsed under the weight of its own physics. But what if there is a more speculative way? One that even pushes the boundaries of physics? What if we don't have to pass through space to get from one place to another? This question brings us to the Alcubierre drive, the warp drive concept. This is a quirk allowed by Einstein's equations of general relativity, but its existence in nature is unknown. This idea is based not on moving the ship itself, but on moving space-time itself. You warp and compress the space in front of the ship while expanding the space behind it. The ship, like a surfer on this space-time wave, is carried forward by space itself without moving at all. For an observer inside the ship is stationary and no laws of physics are violated. But this warp bubble can move space so fast that faster-than-light travel becomes theoretically possible. However, for these equations to work, they require exotic matter with negative energy density. This is a type of matter that repels gravity, and we don't know if it exists. And even the most optimistic calculations show that moving a small ship would require an amount of this exotic matter equivalent to the mass energy of Jupiter. It is a fascinating mathematical possibility, but for now, it is far from a physical reality. Nuclear pulses, fusion rockets, laser sails, antimatter and warp drive, these are all humanity's attempts to escape its cosmic prison. Each offers a different key. One is the key of brute force, another of efficiency, and yet another of manipulating the very fabric of reality. But the truly exciting thing is not what these technologies can do on their own. The truly exciting thing is that they give us permission to ask the ultimate question. If we had a perfect propulsion system, if energy was not a problem, how far could a human lifetime extend? It's time to set engineering aside and explore the absolute limits allowed only by physics and the structure of the universe itself. And now comes the true miracle. Because the engineering is finished, the theories are silent. We now have an imaginary propulsion system. Energy is unlimited. Acceleration is as easy as pressing a button. This is a future where humanity has perfected technology. And in this future, we ask only one question. With this perfect ship, how far into this universe can a human lifespan of 80 years reach? The answer exceeds all expectations. It leaves all dreams behind. Because now we have reached the climax. It is no longer about going to a star system. It is now about the breathtaking, mind-bending, and almost divine mathematics of fitting an entire cosmos into a single lifetime. The tempo is increasing, get ready. The first step, the most modest one, but still a revolution. Our speed, 99% of the speed of light. This is the threshold where the gamma factor reaches 7.1. Our travel time, 50 subjective years. Our passenger will age 50 years while on the ship. So where can they get to in those 50 years? The answer, 350 light years. This isn't a number, this is a world. The sphere within this radius encompasses about 50,000 star systems. Inside are hundreds of stars similar to our Sun, and thousands of confirmed planets orbiting these stars. 350 light years includes some of the most familiar structures in our sky. The Pleiades star cluster is just beyond this distance. A round trip there would take the passenger about 126 years, while for Earth, almost 900 years would pass. How is this possible? Because we're no longer trying to go faster. We're slowing down time. For the first time in history, a human lifetime is long enough to visit thousands of star systems. This is humanity's first real step into the stars, a discovery. But this is only the beginning, because we can go faster. The second step. Now reality bends. Our speed, 99.9% of the speed of light. Our gamma factor has jumped from 7.1 to over 22. Time dilation is no longer linear, it's exponential. Our travel time is still the same, 50 subjective years. So where have we reached now? The answer, 1,100 light years. Understand the magnitude of this leap. We increased our speed by only 0.9%, but our range tripled. This is the theory in its wildest form. What is in an area with a radius of 1,100 light years, millions of star systems, and potentially tens of billions of habitable planets? One of the most iconic sights in our sky, the Orion Nebula, is about 1,300 light years away from us. So, at this speed, within a human lifetime, you can go to that cosmic cradle where new stars are born. You can see newly forming planetary disks. You can witness thousands of newborn stars illuminating gas and dust. These are things seen from Earth as only faint smudges. But you are there. One human life. A single sequence of heartbeats. And you're inside one of the galaxy's most magnificent birthplaces. This should not have been possible. Physics should not have allowed a lifetime to encompass such a vast distance. But it did. Because Einstein's equations offered us the universe's greatest trick. The third step, logic fails. Words are insufficient. Our speed, 99.9999% of the speed of light. The number of nines on the speedometer has increased, and with each 9, the universe has shrunk for us. Our gamma factor is no longer 22, not 223. It's a full 707. Time is no longer slowing down. It's almost stopping. Our travel time has not changed. Still 50 subjective years. Where have we arrived in these 50 years? Are you ready? The answer, 35,000 light years. This means crossing the center of our galaxy and reaching the other side of the Milky Way in a single human lifetime. This is the greatest record in human history. Think, one person leaves Earth, crosses our entire galaxy, that massive spiral structure of hundreds of billions of stars and dark matter from end to end. And this whole journey takes only 50 years for them. When they reach the end of their life, they are tens of thousands of light years from home, in a region of the galaxy no human has ever seen before. How can this be possible? What law of physics does this fit into? This is not the realm of science, but almost of mythology. This journey, fitted into one lifetime, makes Odysseus's journey look like a morning walk. The scientific world was shocked when these numbers were first calculated, because this showed that the galaxy was no longer an obstacle, but had become a playground, the fourth step. And now, we open up to the cosmos. Our galaxy is now small for us. We set our sights on other galaxies, those island universes, our destination, the Andromeda Galaxy. Our nearest major neighbor, the distance, 2.5 million light years. This is a distance the mind cannot grasp. But not for us, because we continue to accelerate. Our gamma factor is no longer in the thousands. but in the tens of thousands, exactly 50,000. Time has slowed down so much that a second is like a lifetime. Our travel time is again 50 subjective years. In these 50 years, we arrive at Andromeda. Feel the weight of that sentence. In 50 years, 2.5 million light years, you celebrate 50 birthdays on the ship. On the Earth you left behind, 2.5 million years pass. The human species on that planet is now in an unrecognizable state. Maybe it doesn't even exist. But you exist, and you are in Andromeda. You're inside a galaxy of 1 trillion stars, bigger than the Milky Way. You're orbiting a larger supermassive black hole. You're under constellations never seen before. This is the greatest discovery, the greatest journey, and the greatest exile in history, because you can never return. Even if you did, there would be no home to return to. This is the most brutal trade-off in physics. It gives you the universe, but in return, it takes everything you belong to. These 4 steps have redrawn the boundaries of a human lifetime. Star clusters, nebulae, the galactic center, and neighboring galaxies all have theoretically become reachable within the lifespan of a single conscious being. But this is not the end of the story, because the universe is much larger than Andromeda, and our perfect ship can still accelerate. So what if we push everything to its absolute limit? What if we try to calculate the absolute, final, physical limit of a human lifetime? And yes, we can push everything to its limit. Because the human mind knows no bounds. We have a perfect ship, and now, with it, we will challenge not just neighboring galaxies, but the universe itself. We will find the absolute limit, the furthest point a single lifetime can touch. And that point is further than even the wildest science fiction writers could have imagined. This is the moment a human becomes a cosmic god. The 5th step, cosmic cities. We're no longer concerned with individual galaxies. We set our sights on galaxy clusters, the mega structures of the universe. Our target, the Virgo cluster, the nearest major galaxy cluster to us. It contains more than 1,300 galaxies, a galactic metropolis. Its distance is a full 54 million light years. This number is measured not by human history, but by the history of life on Earth. Dinosaurs were walking on Earth when this light began its journey. This is an insurmountable temporal abyss. But not for us, because our gamma factor is now in the millions, 1,080,000. Time has almost completely frozen for us. Our travel time is still and always the same, 50 subjective years. In these 50 years, we arrive at the Virgo cluster. When we get there, the Earth we left behind has aged 54 million years. But you are only 50 years old, and you look around. What you see is not a single sky. It's thousands of skies, in every direction. Hundreds of galaxies as large as or larger than the Milky Way are shining. They're orbiting each other. They're colliding with each other. You're in the midst of a cosmic chaos and creation. This is the greatest record in history. For the first time, a human has left their local galaxy group and witnessed the large-scale structure of the universe. How can this be possible? What law of physics can fit geological timescales into the lifespan of a mammal? This is where science ends and philosophy begins. The 6th step, and now we are approaching the absolute limit. Our target is no longer a cluster. Our target is the edge of the universe itself, the horizon of the observable universe. It is a shimmering wall, about 46.5 billion light years away. We cannot see beyond it, because the light from there has not had enough time to reach us since the beginning of the universe. But we can go there. We follow a special route for this journey. We accelerate constantly at 1g, an acceleration equivalent to Earth's gravity. This is the most comfortable and fastest method for the passengers. Halfway through the journey, we turn the ship around and begin to decelerate at the same rate. With this continuous acceleration and deceleration profile, how long does it take us to reach the current boundary of the observable universe? The answer is irrational, heart-stopping. The answer, 45 subjective years. Yes, 45 years, you age 45 years, the universe. In the meantime, ages about 28 billion years, you cut 45 birthday cakes on the ship. In the universe outside, stars are born, galaxies collide, and black holes evaporate. You cross the entire observable universe in less time than a person's normal working life. This is the greatest range humanity can achieve. One lifetime, and the entire known cosmos, 93 billion light-years in diameter. This is beyond any record. This is an absolute victory of human consciousness over physical reality. This should not have been possible. It's like a bug in the rules of the universe. But it's not. It is the rules themselves. But within this absolute victory lies the most brutal and final joke of the universe. A limit, a wall we cannot cross. And this wall is not about our technology. This wall is the expansion of the universe itself. Because the universe is not just big, it is also expanding. And this expansion is accelerating due to dark energy. This means galaxies that are far enough away from us are receding from us faster than the speed of light. This is not a motion. This is the expansion of space itself between us. It's the distance between 2 points growing faster than a ship can cross that distance. This inevitable limit is known as the cosmological event horizon, and it is currently about 17 billion light-years away from us. Everything beyond it is forever unreachable. No matter how fast you go towards it, your target is running away from you faster. It's like an athlete running in the wrong direction on a treadmill. No matter how hard you try, you can never reach the goal. And the worst part, this event horizon is shrinking as the universe expands. Some galaxies we can reach today will be unreachable millions of years from now. The universe offers us a window for exploration, and that window is slowly closing. This is the absolute limit. A human lifetime can traverse a large part of the observable universe. But never all of it. About 94% of the universe is already forever beyond our reach. The stars, galaxies, galaxy clusters, and even the journeys to the edge of the observable universe packed into one lifetime. These are all theoretical possibilities allowed by physics. But at the end of these epic journeys, beyond these mind-boggling numbers and records, it is time to stop and think. Because these journeys are not just about distances and times, they're about the meaning of being human, about connection, loss and exile. To go so far, to live so long, to see so much. What does this really mean for us? The answers to these questions have left us breathless. But now is the time to catch that breath, to slow down and to face the most important question. Beyond all these incredible journeys, these bent times and conquered distances, who are we? What is our place in all this cosmic architecture? This is not a question about speed. This is a question about meaning. Because the greatest paradox of the universe is not how fast a spaceship can go. The greatest paradox of the universe is our very existence. Let's start with the first and most overwhelming paradox: range and limitation. On one hand, we have seen that physics gives us the potential to cover billions of light years in a lifetime. We calculated that one could theoretically travel from one end of the observable universe to the other in 45 years. This means human consciousness has an almost limitless range. A person's mind can touch the light of the most distant galaxy clusters, the most ancient stars. This is a power beyond even our imagination. But, on the other hand, there is a brutal limit the universe itself imposes on us: the cosmological event horizon. This horizon is the point where the expansion of the universe beats our speed, and it shows that 94% of the galaxies we can observe are already beyond this limit, forever unreachable. This is the tragic truth. The universe offers us an infinite playground, and at the same time tells us that the gates to a large part of that playground are closed in our faces. We can see trillions of galaxies, but we can never touch them. Their light reaches us, but we can never reach them. This is the greatest dream and the greatest disappointment existing at the same time. This is a cosmic melancholy. But This is exactly where the beautiful truth begins. Because, yes, we may never go to those galaxies, but we know they exist. We can observe them, analyze them, understand their physics, and stand in awe of their beauty. Our physical range may be limited, but our range of understanding is limitless. Looking through a telescope and seeing a galaxy from 13 billion years ago can be as profound an experience as going there. Because it means the universe has opened its secrets to us, and you're right in the middle of this paradox. Your body is chained to this small planet, but your mind is free to travel to the most distant quasars. You're both incredibly limited and incredibly free, and the tension between these two is one of the most fundamental experiences of being human. The second paradox is perhaps the most personal one: time and the moment. The age of the universe is about 13.8 billion years. Our lifespan at best is 80 to 100 years. When you put these two numbers side by side, our existence is shorter than a cosmic blink. If we were to fit the entire history of the universe into a one-year calendar, all of recorded human history would correspond to the last few seconds of December 31st at 11:59 p.m. Your entire life, all your joys, all your sorrows is a fraction of a second within that last second. This is the tragic truth. We are not permanent in this universe. We exist only for a moment. A moment later, other things will take our place, and no trace of us will be left. For galaxies that have existed for billions of years, our entire civilization is not even as significant as a grain of sand. This is an existential vertigo. It brings us to the edge of nothingness. But then comes that but, and it changes everything. Because, yes, we are only a moment. But that moment is the most incredible moment in the universe. It is the moment the universe becomes aware of itself. After billions of years of silent, unconscious evolution, beings made of stardust appeared on this planet, turned their eyes to the sky, and asked, "What am I? Where is this place?" That brief moment is the moment the universe began to think about itself. We are the universe's way of knowing itself. That 80-year lifespan is a conscious tool the universe uses to understand its 13.8 billion year history. This brief moment is the moment that makes everything meaningful. And you are a part of that moment. Your consciousness is the latest and most advanced link in that billion-year chain. You are the universe itself, listening to the song of the stars, watching the dance of the galaxies, and questioning the meaning of it all. Your short life is not a tragedy. It is a miracle. The third and final paradox is perhaps the most unsettling: connection and loneliness. The most brutal lesson that relativistic journeys teach us is that every great discovery is also a great separation. You can go to Andromeda in 50 years, yes. But when you return, 5 million years will have passed on the world you left behind. This is not just losing your friends and family. This is losing your species, your civilization, everything you know. Every journey is a one-way exile, an exile not just in space, but in time. The tragic truth is this: the closer we get to the stars, the further we get from each other. The greatest explorers are bound to be the loneliest people. They become men and women with no one to tell the story of their discoveries to, people with no past. This is the greatest price of human progress, sacrificing connection. It is to sever those invisible threads that bind us to one another. But the beautiful truth shines again, because this exile is also a new beginning. That passenger who went to Andromeda can start a new branch of humanity there. They become a cosmic farmer, sowing the seed of a species in another galaxy. This is not an end, it is a proliferation. And more importantly, these journeys remind us how precious our connections on Earth are. Perhaps the greatest discovery is not in distant galaxies, but right here, on this planet, in the bond we form with each other. Perhaps the greatest wonder of the universe is not a supernova, but the love one human feels for another. You're also inside this paradox. You also make choices every day. How far will you go to explore, and what connections will you risk in the process? Because each of us is an explorer, and each of us belongs to a home. Range and limitation, time and the moment, connection and loneliness. These paradoxes show that relativistic travel is not just a physics problem, but also a deep philosophical inquiry. But within this inquiry, there is perhaps a more important question we haven't asked yet. This question is not about engines or distances. This question is about choice. On one hand, this incredible potential the universe offers us, and on the other hand, our decision whether or not to use that potential. Because, even if we build the fastest ship, it is still up to us whether we board that ship or not. And this choice is the most fundamental characteristic that makes us human. Now, it is time to consider the weight and consequences of this choice. Let's face a fourth paradox: discovery and home. The human species is by nature an explorer. Our ancestors left Africa and spread across the entire planet. We crossed oceans, climbed the highest mountains, and finally set foot on the moon. The desire to explore is coded into our DNA. Relativistic travel promises the ultimate satisfaction of this desire. To see other star systems, to walk on alien planets, to bathe in the light of other galaxies. This is humanity's greatest adventure. But this adventure has a tragic price. That price is home. Every road to the stars is a road away from Earth, and because of time dilation, there is no return from this road. An explorer going to Andromeda may be carrying the future of humanity to another galaxy, but they are also leaving their own past, their own family, their own species, their home forever. They are no longer an Earthling, they are a cosmic orphan. This is the moment where the greatest victory is intertwined with the deepest loss. But that beautiful but comes into play here too, because maybe home is not a geographical place, but an idea. Maybe that passenger going to Andromeda is not leaving Earth, but on the contrary, is immortalizing Earth by carrying its idea, its consciousness, and its memories to another corner of the universe. Maybe home is not a planet you leave behind, but the memories you carry inside you. This is the deepest meaning of discovery, to set out not to find new places, but to preserve the old one, and you are a part of this choice. You too leave your home for small discoveries every day, and you return every day. But what if one day you had to embark on a journey from which you could not return? Which value would you hold higher? The thrill of discovery, or the warmth of home? This brings us to a fifth and final paradox: knowledge and meaning. The greatest thing these journeys promise us is knowledge. The opportunity to learn how the universe works, whether there is life on other planets, the secrets of black holes, how galaxies form. This is the potential to find answers to the most fundamental questions humanity has been asking for thousands of years. With a perfect ship, we would have access to the universe's greatest library. This is the pinnacle of knowledge. But the tragic truth is that knowledge does not always bring meaning. You can measure the mass of the black hole at the center of Andromeda. This is knowledge. But what meaning does this knowledge add to your life? You can catalogue thousands of alien worlds. This is also knowledge. But does this eliminate the feeling of loneliness? It could even be the opposite. As we learn how vast, how empty, and how indifferent the universe is to us, we may face the meaninglessness of our own existence. This is the greatest sorrow knowledge can bring. Finding the answers, but not finding meaning in those answers. But then, that final and most powerful but arrives. Because meaning is not something we discover. Meaning is something we create. The universe itself may be meaningless, but our view of it, our effort to understand it, our writing poems about it, painting pictures, composing songs, these are the things that give meaning to a meaningless universe. Meaning is not in the numbers or the equations. Meaning is in the eyes of the person looking at those numbers. Meaning is in the mind of the person who writes those equations. And you are a part of this meaning creation process. You too look at a world that might be meaningless every day, and you create your own small meanings. The meaning of a friendship, the meaning of a sunset, the meaning of a piece of music. This is our greatest power. What makes the universe meaningful is not the universe itself. It is us. When you think about all these paradoxes, all these contradictions, how do you feel? On one hand, there is the mind-boggling vastness of the universe and our smallness, like a dust mote in the ocean. This can bring a sense of nothingness, of meaninglessness. But, On the other hand, there is the ability of that dust mote, us, to understand that ocean, to think about it, and to be amazed by its beauty. This can bring a sense of power, of miracle. Which is true? The answer, both. To be human is to constantly oscillate between these two feelings, to know that we are nothing, and to feel that we are everything. To be the most insignificant part of the universe, and to be the most important moment when the universe becomes aware of itself. This tension is our tragedy, and at the same time, our triumph. Now we know our range is limited, but our understanding is limitless. Our life is a moment, but that moment can illuminate the universe. Our connections are fragile, but we have the power to rebuild them. Our legacy is temporary, but our ideas are permanent. And the silence of the universe is overwhelming, but our music gives meaning to that silence. All this philosophical journey, all these thoughts, have brought us to a single point, to where we started. But now we look at it with different eyes. This is the end of our journey about how far a lifetime can go. And now, with all that we have learned, it is time to stop one last time and look at this incredible cosmic landscape. And so now we face a deeper question. Because the issue is no longer what our place is in the universe. The issue is what this knowledge does inside us. How does knowing we are part of a universe so vast, so old, so indifferent, change us? This is not a question to be answered with telescopes or equations. This is a question we must turn inward to ask. Because the greatest secret of the universe may not be hidden in distant galaxies, but in the depths of our own consciousness. First, let's consider this paradox: choice and fate. On one hand, relativistic travel offers us an almost infinite freedom of choice. Choose your speed, choose your gamma factor, and thus choose the future you will arrive in. If you choose to go to Andromeda, you choose to arrive 2.5 million years in Earth's future. If you choose to go to a nearby star and return, you might choose to return to an Earth only a few hundred years in the future. Each journey is a door to a different future. This is the power to write our own destiny, the potential to be masters of time. But this absolute choice has a tragic twin: absolute irreversibility. Because you can only go forward in time, every choice you make means an infinite number of other doors you have closed. The moment you choose to go to Andromeda, you have forever given up on 2.5 million years of history on Earth, on the descendants of your loved ones' descendants, on all of humanity's triumphs and tragedies in that interim period. You cannot go back. You cannot change your choice. This is the heaviest burden of freedom. Every decision is a farewell. But the ray of hope shines here, because this irreversibility also makes every choice incredibly precious. Every step you take on a one-way road is more meaningful, because you know that moment will never be lived again. This teaches you not to postpone life, to appreciate every moment. Every decision of the traveler is a permanent signature etched into the fabric of the universe, and you live this paradox every day. Every choice you make means an infinite number of other lives you did not choose. You are the captain of your own time journey, and every day you are traveling towards a future from which you cannot return. Does this scare you, or does it make every moment more precious? This leads us to another deep thought: legacy and oblivion. One of the most fundamental laws of the universe is that everything will eventually perish. Stars die out, galaxies disperse, even the universe itself may one day reach a heat death. On this cosmic scale, our desire to leave a permanent mark behind seems tragically futile. Consider the Voyager probe. With that golden record carrying the sounds and images of humanity, it drifts among the stars for tens of thousands of years. But even after 70,000 years, it will not have reached the nearest star, and eventually, when its power sources die, it will be lost forever as just a silent, dead piece of metal. What will remain of our civilization, of our greatest achievements, is a cosmic speck of dust. This is the inevitability of oblivion. Everything we do, every book we write, every city we build, will eventually be erased in the vastness of time and space. But that but takes the stage once more. Because legacy is not a name carved in stone. Legacy is an idea that is passed on, Our physical existence may be temporary, but our understanding, our knowledge, our art, our love, continues to live as long as it is passed on to the next generations. Voyager's golden record may never be found by an alien, but the spirit of curiosity and hope that created it will exist as long as the civilization that launched it lives. Our true legacy is not the things we build, but the thoughts we inspire. And you are a link in this chain of legacy. You have received the knowledge of those before you, and you will pass something on to those after you. Your life is a chapter in that great and continuous story called humanity, and that story may be as permanent as the universe itself. And finally, the most personal paradox: wonder and habit. Everything we have talked about on this journey has been mind-boggling, astonishing facts, the bending of time, intergalactic travel, the size of the universe. When first exposed to this information, one experiences a shock, a sense of awe, of wonder. One realizes what an incredible place the universe is. But the human mind has a tragic feature. It gets used to even the most incredible things over time. Today, we know that every point of light shining in the sky is a sun that could have its own planetary system. This was information that would have driven a person living just a few centuries ago insane. But for us, it's a commonplace fact, a line we hear in a documentary. The sense of wonder, over time, gives way to habit. The miracles of the universe get lost in the noise of daily life. This is one of the greatest tragedies, to become blind to the infinite beauty the universe offers us. But that final but offers us a way out. Because wonder is not knowledge, it is a choice. You can choose to look at the sky every day and see it not just as a ceiling, but as a window opening to billions of worlds. You can choose to hear every new scientific discovery not just as news, but as a new secret the universe is whispering to us. Keeping the sense of wonder alive requires effort. It requires curiosity, a childlike excitement, and you have that choice. Every day, you decide whether the universe is ordinary or miraculous, and that decision determines your relationship with the universe. Choice and fate, legacy and oblivion, wonder and habit. These thoughts show that the universe offers us not only a physical home, but also a philosophical mirror. When we look into that mirror, we see not only stars and galaxies, but our own deepest fears, hopes, and potentials. But there is one more reflection this mirror shows us, perhaps the most important one, and that mirror shows us one final reflection. This reflection is about the nature of the universe itself. Because, throughout this journey, we have seen the universe as a distance to be overcome, an equation to be solved, a destination to be reached. But what if the universe is not a destination? What if the universe itself is the journey? This is the final philosophical layer that changes our entire perspective. This brings us to this paradox: purpose and process. The human mind is by nature goal-oriented. The end date of a project, the finish line of a race, the destination of a journey. We always look for an end. Relativistic travel is the greatest example of this search. Our goal is to reach Andromeda. Our goal is to see the center of the galaxy. But this focus on the goal has a tragic consequence: missing the journey itself. On a journey lasting hundreds, thousands of years, if the sole focus for generations of crew is the arrival, then the countless sunsets, the countless starscapes, the countless human interactions that happen in between become meaningless. Life becomes a waiting room, sacrificed for the sake of a destination. This is the tragedy of purpose consuming the process. But that beautiful but whispers to us. What if the real purpose is not to arrive? What if the real purpose is the act of being on the way? A spaceship is not just a vehicle, it is a world in itself. New generations can be born on that ship, new works of art can be created, new philosophies can be developed. Perhaps the real purpose of an interstellar journey is not to colonize another planet, but to see what humanity becomes during that journey. This is turning the process into a purpose, and you live this paradox every day. You may be living your life focused on the next goal, the next achievement, the next vacation. But on the road to those goals, life itself is flowing by, and maybe real happiness is not at the finish line, but in every single step you take towards that line. This also leads us to this thought: control and surrender. The entire history of human civilization is a story of our effort to control nature. We controlled fire, we controlled rivers, we controlled the atom. Relativistic travel is the pinnacle of this desire for control, bending time, annihilating distance, turning the rules of the universe to our advantage. This is playing God. But this desire for control has a tragic limit. The things we cannot control the expansion of the universe. We cannot cross the event horizon. We cannot control when a star will go supernova. The universe, eventually, reminds us that we are not the boss. This is the collision of human hubris with cosmic reality. It is a bitter reminder that no matter how far we advance, we're still a small and fragile part of this universe. But that beautiful but says that the opposite of control is not chaos, but surrender. Surrender is not giving up. Surrender is the wisdom to accept what you cannot control and focus your energy on what you can. You cannot stop the expansion of the universe, but you can make your own small world within that expanding universe a better place. You cannot control the fate of the stars, but you can control your own reactions and choices. This is the deepest form of power, knowing when to fight and when to go with the flow. You are also seeking this balance. There are things in your life you can control and things you cannot, and the key to happiness lies in understanding the difference between the two. And finally, the place where this whole journey has brought us: silence and music. When we look at the universe, our first impression is of an overwhelming silence. The space between the stars is cold, dark, and silent. This gives a sense of cosmic loneliness. On this huge stage, our voice, our song, seems like nothing. This is the tragic silence of existence. Against the noiseless dance of billions of galaxies, our entire history is not even a whisper. But then, that final but comes, and it reminds us that music is not the absence of noise. Music is meaningful sounds placed within silence. The universe itself provides a silent background, but we compose our own music, our own story, our own meaning upon that silence. Science allows us to understand the notes of that music. Art allows us to express that music. Philosophy allows us to question why that music is important. We are the composers of the universe. We are the beings that give meaning to that silence. And you are a part of this orchestra. Your life is a unique melody played in that great cosmic symphony. And that melody changes the silence of the universe forever. Now we know. This journey has shown us not only how vast the universe is, but also how resilient we are in the face of that vastness. Our range is limited, but our understanding is limitless. Our life is a moment, but that moment can illuminate the universe. Our connections are fragile, but we have the power to rebuild them. Our legacy is temporary, but our ideas are permanent. And the silence of the universe is overwhelming, but our music gives meaning to that silence. This entire philosophical journey, all these thoughts have brought us to a single point, to where we began. But now we look at it with different eyes. This is the end of our journey about how far a lifetime can go, and now, with all that we have learned, it is time to stop one last time and look at this unbelievable cosmic landscape. And now, we look at that final landscape. On this journey, we began by seeing how slow humanity's fastest vehicle is on a cosmic scale. But then, with a key given to us by Einstein, we discovered that we could bend time itself and fit entire galaxies into one lifetime. We weighed the cost of this mind-bending potential, the philosophical weight of loneliness, separation, and irreversibility. For each of us, we saw our own reflection, our own paradoxes, in the giant mirror of the universe. We know now that the ultimate limit of a human life is not the 80 years on a calendar, but the speed it can reach. Because speed creates time itself. This is the greatest proof that human consciousness can challenge even the most rigid-seeming limits. The universe did not build us a prison. It offered an incredibly vast playground for those who understand its rules. The potential to cross the 2.5 million light-year distance to Andromeda in just a few subjective years in this playground is beyond even humanity's imagination. You are a part of this universe. You have your own time, your own journey. And perhaps the greatest lesson of this journey is not how far we can go, but how much meaning we can pack into the moment. wherever we are. Because, even in the most distant galaxies, the only thing we will search for is that connection, that wonder, and that love we already have on this small blue planet. If this journey has given you a new perspective on the universe and our place in it, consider subscribing to the channel and sharing your thoughts with us. Because this conversation is a journey of discovery we're all making together. But in this journey of discovery, we noticed a final limit, an insurmountable wall, the cosmological event horizon. But what if this final obstacle is not just a simple limit of distance? What if what's stopping us is a mysterious and irresistible force, pushing the universe itself away from us, and with increasing violence? On this journey, we saw that we could conquer distance by bending time, but there's something I didn't tell you. The universe isn't just expanding, it's accelerating. And behind this acceleration, there is an invisible force, the exact opposite of gravity, tearing everything apart. Its name, dark energy. On our next journey, we will discover the secret of this force that makes up 68% of the universe, and the end it is dragging us towards. Are you ready?